Hey everyone, welcome to our Ripple Tank post-lab video, take 2. We had a bit of an interruption from our friendly afternoon announcement, matey. But we're going to give it a take 2, and I just want to talk some basic things about wave speed, wavelength, frequency, and amplitude. The three big terms are reflection, refraction, and diffraction, and then I'll show a diagram of interference. And then we can go over these properties in class, and I'll show you some videos of the world's greatest ripple tank. But for right now, it's just some basic principles that hopefully you got to see in the ripple tank lab. In terms of the basic wave properties, the first thing I wanted to mention is that wave speed is determined just by the medium. And in your lab, the medium is simply the water depth. And we're only using water, and if you change the depth, you'll change the medium, and therefore change the speed of the wave. One thing that will not influence the speed of the wave is the amplitude. Now, you can make a bigger amplitude by pushing in the water more. What that will do is it will change the energy, but it will not impact the wave speed. One of the things you can change is the frequency, and the frequency is just the number of waves that you make in a given amount of time. And the way that you control the frequency is by changing the motor speed. Controls the frequency. So making the motor go faster means that you'll get more waves, and as a result of that, if you make more waves, one thing that you'll decrease is the wavelength, because frequency is inversely proportional to wavelength. So if we made a wave that is very frequent, as I'm drawing right here, you can see that the distance between crest to crest is not very large. However, if we made a wave that is not very frequent, the distance between crest to crest is much larger. So as frequency increases, wavelength decreases, or the other way around. One of the three big properties in the lab is reflection. And reflection is the bouncing of a wave off of a barrier, or simply bouncing. And I just want to draw a little picture of reflection. So imagine the ripple tank lab, and we put a barrier on an angle, and I'm going to draw three little wave fronts moving towards this object. The waves are going to bounce off, and they're going to bounce off towards the right. Now, your picture in the lab was probably very clouded because there's lots of waves going all over the place, but if we were to just simplify it, it would look like this. And the way we know that this is going to bounce off is by drawing a little line in, and if we draw a dashed line that is perpendicular to our barrier, we call this a normal line. That may sound familiar from friction and inclined planes. Normal means 90 degrees to something. And we measure this angle right here. We call this angle theta I, and that is referred to as the angle of incidence. That will equal the angle that the wave comes out at, which we call theta R, and that's the angle of reflection. So theta I equals theta R. And this is also known as the law of reflection. So the law of reflection is the angle of incidence equals the angle of reflection. So if one wave comes in at 20 degrees, it leaves at 20 degrees. If one wave comes in at 60, it leaves at 60. The last thing I want to mention about reflection, and you'll see this as a common theme in this video, is how does reflection affect the velocity, the frequency, and the wavelength? Well, it turns out that reflection doesn't impact these things at all. They remain constant. Nothing changes about a wave when it reflects except its direction of traveling. So velocity remains constant, frequency remains constant, and wavelength remains constant. So there are some of the basics of reflection. The second biggest property in the lab is refraction. Refraction is the bending of a wave as it passes from one medium into another of a different density. Key word here, bending. The picture that I want to draw of refraction is going to be, this line represents a barrier from shallow water to deep water. And imagine that we had our wave traveling in deep water where it travels very fast. And then it goes into shallow water where it travels slow. Because these wave crests are connected, when the crest reaches the slow water, it will slow down. But the part that's still in the fast water will race ahead, and it will cause it to bend a little bit. So the wave actually travels in a different direction. And that's what we call refraction. And if we look at our three big properties that define the wave, the velocity, the frequency, and the wavelength, the velocity when it goes into the shallow water is going to decrease. It would increase if it were going into deep water. The frequency remains constant. That's the one thing that never changes unless you change the motor speed. And the wavelength is also going to decrease. And as a result of this slowing down, it bends, and that's refraction. This is only for, let's put a star here, shallow, or maybe we'll write deep to shallow water. Those would switch if it went the other way. So that's refraction, the bending of a wave. Third property is diffraction. Diffraction is the spreading of a wave as it passes through an opening. Keyword, spreading. If I take a wave and send it through a small opening, so here are some wave crests, they're moving towards this opening. They don't just get blocked by the opening, some make it through and they spread out to fill in the region behind the opening. We call this the spreading of a wave. And if we were to look at our three measurements of the wave, the velocity would remain constant. When a wave diffracts, the frequency would remain constant because we don't touch the motor, and the wavelength remains constant. So with diffraction, all we're really doing is changing the direction of the wave again. We're just spreading it out behind the barriers when we squeeze it through that small opening. The final thing that you saw in the lab was what we call an interference pattern. Here comes our the interference pattern. There's two types of interference. There's constructive interference and destructive interference. The pattern that you saw in the lab shows both of these types. Constructive interference is when crests meet crests and troughs meet troughs. And if you look down on this diagram, we had two sources. And anytime a bold line meets another bold line, that's a crest meeting a crest. And a thin line meaning a thin line is a trough meeting a trough. So you get very high crests and very low troughs. And these are areas of constructive interference, indicated by the red dots. The blue dots are what are of great interest to us because these are the areas of destructive interference where a crest meets a trough. And you can see they kind of create these lines. I'll try to trace them out here. And these lines radiate outward from the sources, and this is what creates our interference pattern, areas of constructive and destructive interference. And at these destructive interference areas, the water is totally flat because the crest is meeting a trough, essentially leveling it out. So there are the basics from the Ripple Tank Lab. We had some things about wave speed, wavelength, frequency, and amplitude. Reflection is bouncing. Refraction is, let's write that, bouncing. Refraction is bending. Diffraction is spreading. And interference, constructive or destructive, is the combining of waves. So hopefully that helps a little bit, and if you have any questions, you can make sure you put them in the survey after you complete it and then bring them to class tomorrow, and I'll show you some videos from the world's greatest ripple tank to kind of display these things. Thanks. Goodbye, everyone.